Hi students, so in the last video we showed that if you had a sinusoidal signal for your voltage, that can be written as V of t is V max times the sine of omega t. Now I wanted to show you if in your function you have a constant being added to this omega t inside the parentheses, this is plus phi in this example, then this phi here will be the phase shift. And what that means is that if we had our signal here, a sine wave is going to start at the origin. So here's one period. So that makes this point here period over 2. What the phase shift is going to do is it's going to shift it either to the left or to the right. And so what I like to do is I like to find little fiducials on this sine wave, like where it crosses at 0 and again when the next period starts and period over 2. And I take this point and I just will either move it to the left or move it to the right. So the way it works is if you have a plus phi, that's going to correspond to moving the signal. Move like this graph shape, move signal to the left. If you have a minus phi, then you're going to move the signal graph shape to the right. So in this case here, since we have a plus phi and our sign here is positive, what that means is we're going to take one of the points that is crossing, like the 0 crossing, and then we're going to shift that point over by this amount phi. So our sine wave ends up being, once we move it, is going to be like this. So everywhere is going to be behind or lagging by this phi here. So this is our original, and then this is our phase shifted. Graph of our signal. Okay, so it's interesting because if you phase shift enough, you can imagine this dotted signal. If you phase shift it all the way by pi over 2, then your signal is just going to be basically your original signal flipped upside down about this x-axis. The other thing is if we shift it by an entire period, then our signal is just going to land directly on where it was originally. So if we phase shift enough from our starting point, we can actually come up with some identities for where our graph is going to land relative to where it started. So these are the identities. The first one is if we have a sine omega t plus or minus 180 degrees, so basically this is pi over 2, then this is going to flip our sine wave upside down. Okay, so it's like we would be multiplying by a negative. So if we started with this original place, if we phase shifted by either to the left 180 degrees or pi over 2, or to the right by pi over 2, then we're going to land basically exactly underneath our original graph. Okay, just as if we were multiplying by a -1. Then similarly, if we have the cosine omega t, if we phase shift this by half of the period, then this is going to be negative cosine omega t. So same thing if we have a cosine graph. If we start here, there's one period of the cosine, then if we phase shift by 180 degrees, then our cosine is going to end up like this. So just basically flipped, it looks like it's flipped upside down. In other words, multiplied by a negative. All right, the next one that's going to be useful is if we phase shift by 90 degrees, then this is going to be plus or minus the cosine of omega t. So in other words, if we apply a phase shift of 90 degrees to a sine, it's going to turn that into a cosine. So if we start with a sine starts here at 0 and goes like this. If we phase shift by 90 degrees, then this peak here is now going to be starting right there, just like the cosine would. Okay, so it becomes a cosine. This plus or minus indicates that if we phase shift by positive 90 degrees, we'll have a positive cosine. If we phase shift by minus 90 degrees, then we'll have a negative cosine. All right, so then this one is similar but a little bit different. If we have the cosine and we phase shift by 90 degrees, then we end up with the sine, but in front of this we have a minus plus the sine of omega t. So we can turn the cosine into the sine, but the way it works is if we phase shift by a positive 90 degrees, then we get a negative sine. If we phase shift by a negative 90 degrees, we get a positive sine. Okay, so the sign of the sine is going to switch. So the next thing I kind of want to mention to you is this idea of periodicity for our signals. And that is that mathematically it looks like this. So any function of t, if you take that function and if you add to it any integer times the period, then you're going to get that original function back. So if we made the graph, here's our sine wave. Anywhere along this graph, let's say like this point, at this f of t, if I add to it 1 times the period, that's going to put me right here. And for any point along this function, it's going to be, there we go, it's going to land on basically the exact same point. Oh, I didn't draw this right. This point is right here. Okay, so between this point and this point, it's in the same location on my sine wave relative to where it begins. This differs by 1 period. Okay, it's a little bit easier to see. From this zero crossing to this zero crossing is also 1 period. This zero crossing to this zero crossing, the distance here is 1 period. So from any point on our, basically our original f of t, if we add to it n times the period, we're going to end up in that same y coordinate position, okay? And here I'll just clarify, this is where n can be any integer. So let me know if you have any questions about periodicity and how phase shift can kind of turn sines and cosines into each other or flip them upside down.